Hi, I'm Saaketh. I'm a junior in high school and I'm excited to present my project, Revolutionizing Lunar Landings with Deep Learning and Reinforcement Learning. I pursued this project because I've always had a passion for computer science as well as aerospace engineering, and I wanted to fuse the two together to reveal the vast impacts AI can have on space exploration. This project utilizes an AI model that I built through Python to help lunar vehicles locate a safe and flat landing spot on the lunar surface. As most of us are familiar with, the Apollo 11 mission was the first successful lunar landing mission taking place on July 20th, 1969. It was a manned mission featuring Neil Armstrong, Buzz Aldrin, and Michael Collins, who successfully landed on the moon, and two of them even walked on it. Although it was a huge success for our country, the reality of the mission was far more challenging than many of us anticipated. The spacecraft's poor computer guided them into a field filled with rocks and boulders, and they were headed directly towards it upon landing. At only 1,600 feet above the lunar surface, Neil Armstrong's quick thinking saved the crew as he maneuvered the spacecraft away from disaster. Many lunar missions have taken place since the Apollo 11, but among all the challenges faced, lunar landing is still the biggest one. A more recent attempt was taken by India with the Chandrayaan-2 model launched on September 7, 2019. It was an unmanned mission that ended fatally when the Vikram lander hard crashed into the lunar surface. This just shows that even with the huge technological advancements made since the Apollo 11 mission, lunar landing is still a prevailing problem today. So what makes the lunar surface so hard to land on? Well, the moon is a very hazardous environment. Its surface is littered with large moon rocks and boulders. The lunar surface composition is made up of large mountains, huge impact craters, and mareas, which are large basins containing water flow. These compositions make lunar landing a daunting task for humans, even in today's age. To address this lunar landing issue, the best fit model was used, artificial intelligence. The reason why AI works the best is because it offers a new solution that surpasses human limitations in processing vast amounts of data. It also makes real-time decisions far more accurate than we ever could. The human mind can only do so much, but by leveraging AI capability of data analysis, this project reveals a developed model that can autonomously detect safe landing spots. The specific AI method that I used was reinforcement learning. Reinforcement learning is an AI model that uses data and algorithms to imitate the same way humans learn. This system contains two objects, an agent and an environment. The agent is the one taking actions within an environment and is the learner of the system. The environment is an external system in which the agent interacts with. The environment, the agent learns through these interactions through trial and error, in which reward is positive and negative feedback to the agent. This example on the right is a great example of a reinforcement learning model. We have our agent, we have our environment, and the first thing the agent does is make an observation within that environment. Based on this observation, it will take an action which it predicts will be the best. Based on this action taken, we reward it with a positive and negative feedback to let the agent know if that action was good and it should keep doing it, or if it's bad, it should do something else. And this is basically how the agent learns. Now for the moon lander, a custom environment is used. Figure 2 on the left shows a topographic elevation image of the entire moon. This is the environment our agent will interact with and will locate that flat landing spot. If you look closer, there are thousands of little pixels, and each of these pixels hold a numerical value, and that represents the elevation image at that area. Now, for real-time missions, our rover wouldn't be using an entire map of the moon, since that landing range is way too big. To simulate the case of a real-time mission, I zoomed in and selected little random spots on the map, as if the rover was going to land there, as shown in Figure 3. This simulates a more realistic landing zone for a rover during a lunar mission. The next component of our moonlander is our agent, which is the entity taking actions within that environment. Our agent is able to move up, down, left, and right, and it will use that to explore and understand the elevation data of that specific region. Once it understands that data, it will use that data to locate that flat landing spot. A fifth action is also passed through called terminate, which basically just signals that our agent has already found a flat landing spot and it just doesn't need to move anywhere else. Once that is done, the reward function evaluates our agent's actions. It analyzes the action taken by the agent and gives a reward depending on how desirable the action was. The first thing I do is take account of all the surrounding values for our agent because we want a flat landing spot with the greatest area. Next, I take the mean for that region, determine the average elevation chunk, and evaluate how flat the area actually is. Next, we deviate the agent from the average values. This measures how much of the surrounding terrain varies from being flat. Finally, a threshold 100 is set and the reward is calculated. A 0 was also passed through to make sure there are no negative rewards, and if the agent does something we do not desire, we would just give it no reward. This reward function accurately analyzes the surrounding flat landing spots relative to the agent's location. Now that the base of our model is created, it's now ready to train. The training model that I used was Stable Baselines 3, which is reinforcement learning algorithms based on OpenAI Baselines library. A baseline is just a method used to create a prediction for a data set, and it helps our agent make an action. The main algorithm that I used was DQN, which predicts the value of possible actions given a particular state. Next, I use an MLP policy, which interprets state information to predict an action. An MLP policy is basically when the agent is ready to take that action, it utilizes its observations and form a prediction for what action it should take. Once all that is done, an evaluate policy function is passed through to evaluate the agent's performance after training. This data set on the right is what that evaluate policy function gives us. It gives us different information such as episode reward mean, episode length mean, and this is where I evaluate the agent's performance and make sure it's doing what it's supposed to. Now, these are the results shown by the Moonlander. As shown, the fully trained model is effectively capable of finding a flat landing spot as located by its high reward. The model is also very efficient as seen by the spike in reward in the shortest amount of iterations. When I first started training this thing, it took a lot more iterations to get that max reward. But over time and the reward function utilized, it got better and better and took less and less iteration to get that spike in reward. In conclusion, this project reveals the beneficial integration of AI within space exploration. As AI was successful in locating flat landing spots, which drastically increases success rates of these missions and overall safety of these missions. My future plan is to move beyond the path of mission landing and utilize the AI to plot safe and traversal paths. Since the AI is already using elevation data, it is able to utilize that same data to create traversal paths for rovers to move around the moon and create those flat points. In all, the power of AI within future space exploration methods is boundless, and this project serves as a beacon of light, revealing the capabilities that AI can have on space exploration. Thank you.